I'm going to be making a series of videos on problems on integration. The first problem was taken from the book Pure Mathematics for Advanced Level by Bunday and Mulholland, published in 1967. So in this problem, we've been given an integration of an algebraic expression here. And what we're asked to do is to do the integration by substituting for x with tan theta. There are actually two substitutions, but let's take the first one. So x is equal to tan theta. So if x is equal to that, then the dx would be secant square theta. So if you don't remember this by heart, I remember this as a formula in India while doing my A-levels. So if I don't remember that, what I can always do is I can go back to the basics, which is d of u over v with v u dash minus u v dash upon v square. And tan theta is sine theta over cos theta. So we can arrive at this secant square theta also using this expression sine square theta plus, we need this as well, the trigonometric identities. So from this we can get dx is equal to secant square theta, and 1 plus, so 1 plus x square would be 1 plus tan square theta, which is same as secant square theta as well. Again, you can solve this using basic trigonometric identities. So let's substitute this back into this expression above. So we've got x cubed, so it's going to be tan cubed of theta. Oh, I missed the d theta here. Divided by 1 plus x square. 1 plus x square is secant square theta, and there is a cubed here, so it's going to be secant square theta whole cubed, and then the dx would be secant square theta, so secant square theta d theta. So you've got this expression. So you've got a square and then a sixth power here, so which reduces to tan cubed theta divided by secant to the power, let's say, of 4 theta d theta. So I can rewrite this expression as sine cubed theta divided by cosine cubed theta, and I can write secant to the power of 4 theta as cos to the power of 4 theta d theta. So it simplifies very nicely as sine cubed theta cos theta d theta. So I can now substitute for sine theta as, let's say, another variable called z. Then I can say that cos theta d theta should be equal to dz. So this is to make our life simpler by doing the integration by substitution for the substitution. So what we get now is integration of z cubed dz. So we have reduced a trigonometric integration problem back to the algebraic problem. So we started with algebraic, we converted to trigonometric, we are back to algebraic. So which is straightforward, z to the power 4 by 4 plus constant. So I'll add a new layer. So the integration, the answer is z to the power 4 by 4 plus constant. But we started off with z as sine theta. So sine 4 to the power of theta divided by 4 plus constant, that would be the integration of the problem that we started with, that whole expression. But we want the answer in terms of x, not in terms of theta. So originally we started off with the expression x is equal to tangent of theta. So we would like to convert the thetas back to x. So let's again do further simplification. So x should be equal to sine theta divided by cosine theta. So x to the power 4 would be sine to the power 4 theta divided by cos to the power 4 theta. Right, so we can substitute for sine to the power of 4 theta with x to the power 4 cos to the power 4 theta by 4 plus c. So again, we have to get rid of this cos to the power 4 theta, and we can do that by simply rewriting that as cos square theta whole square 1 minus sine square theta. And okay, see that's not leading us anywhere, so let's go back and do some more simplification. So we've got x is equal to tan theta, so let's add the same thing. 1 plus x square should be equal to secant square theta. So 1 over 1 plus x square should be equal to cos square theta. So then from which we can find out the cosine to the power 4, and what we get now is x to the power 4 divided by 4. Cos to the power 4 would be this 1 by this whole expression square, so it's going to be 1 divided by 1 plus x square whole square plus constant. So that's the answer that we are arriving at.